Okay, please go, Mari.
Hello, everyone. It's my pleasure to be chairman of this session. And as you can see, our speaker is Gleb Kotousov. He's originally from Canberra, actually. He was did his PhD. It was a joint one, I believe, between ANU and Rutgers, and his supervisors were Vladimir Bajanov and Sergei Lukyanov. And then he went off to a postdoc in Hamburg, and he's there for a while yet, I guess. And so it's my pleasure to listen to his talk. And as you can see, it's called excuse me, density of states for an integrable spin chain. Thanks a lot. Good.
All right, thank you, Mari, for that introduction. And also, before I start, I'd like to thank the organizers for giving me this opportunity of presenting my research. So, in the mid 20th century, one of the reasons why integrable exactly solved models and statistical mechanics were of interest came from the theory of critical phenomena. And in particular, exactly solved models provided a setup where numerical methods and approximate methods could be tested, and ideas such as important concepts such as universality and scaling could be sharpened. And one of the ideal laboratories to study and understand these concepts are in critical integrable one-dimensional spin chains. And in this context, one studies the scaling limit of these spin chains. This is sort of a limit where the size of the spin chain is kept fixed and the lattice spacing is shrunk to 0, or which is equivalent, the number of lattice sites tends to infinity. And in taking the scaling limit, one only considers the low energy excitations. Then if the spin chain is critical, conformal invariance predicts this sort of structure for the low energy excitations above the ground state. So of course, energy is an extensive quantity. So there's this term proportional just to the volume, where E infinity is the specific bulk energy. This term is not very interesting from the point of view of the study of critical phenomena. In particular, it's not universal and depends on the microscopic interactions of the Hamiltonian. The Fermi velocity here, this coefficient, is also not particularly interesting and non-universal. However, a term in the brackets here turns out to be universal and is governed or described by a conformal field theory. So the structure of this term is the following. So you have primary states, corresponding to L plus L bar is equal to 0. And they're labeled by these conformal dimensions, delta and delta bar. And above each primary state, there's a whole tower of excitations where these L and L bars take all positive integer values. The space of states, of low energy states in the scaling limit, organizes into, well, it can be decomposed into highest weight irreducible representations of the Virasoro algebra or extended algebra of conformal symmetry, where the highest state corresponds to sort of the conformal primaries, where L plus L bar is equal to 0, and the descendants are the states where corresponding to non-zero L and L bar. One of the sort of standard examples is the XXZ spin chain, where you can see this structure, the scaling in detail. The XXZ spin chain is a one-dimensional spin chain where at each lattice site you have a quantum mechanical spin. And the spins interact via just the nearest neighbor interactions. So in particular, sigma xm here is the Pauli matrix that acts on site M of the lattice. The XXZ spin chain is anisotropic. And the anisotropy is parameterized by this constant or coupling J. The standard notation for this coupling is actually delta, but in my presentation, delta has already been reserved for the conformal dimensions. So I'm going to use J here instead. The XXZ Hamiltonian can be considered on the with periodic boundary conditions, which corresponds to the one-dimensional chain being sort of a ring, where the n plus first site and the first site are identified with each other. In fact, it turns out, just technically, it turns out to be easier, rather than considering periodic boundary conditions, to consider quasi-periodic boundary conditions, where the Pauli matrices on the n plus first site and the first site are identified, but there's this extra twist here, parameterized by k, which takes values from -1/2 to 1/2. The physics of the Heisenberg XXZ chain depends a lot on the value of this coupling J. So in particular, if J is large and positive, the ground state is ferromagnetic. If it's large and negative, then it's anti-ferromagnetic, where the spins tend to anti-align. However, it turns out that when J takes the values from -1 to 1, the XXZ, the lattice model, is critical and has a universal behavior that's described by conformal field theory. And in this regime, the so-called disordered regime, it's useful to parameterize the coupling's constant J by this angle gamma. So the low energy spectrum of the XXZ spin chain in the disordered regime has been studied in a number of works. And it takes the form here. Well, delta and delta bar are given by these expressions, and SZ and W are just integers. Let me just take a moment to explain the meaning of these integers, SZ and W bar. So the Hamiltonian, XXZ spin chain Hamiltonian, commutes with the Z projection of the total spin operator, this matrix here. And so it has block diagonal form, and each block is labeled by the eigenvalue of SZ. And this SZ is precisely the same as Z that comes into this, comes in over here. The situation with W is more tricky. So W is the integer W can't actually be assigned to the states similar to SZ, and it can only be assigned to the low energy states, low energy part of the spectrum, and strictly speaking, it only makes sense in the scaling limits. It always occurs in this combination with K, so there's always K plus W, and it's referred to as the winding number. This sort of discrete spectrum of scaling dimensions has a natural interpretation in conformal field theory, and it's well known that the scaling limit of the XXZ spin chain is governed by a free massless compact boson. So a free massless compact boson can be written as the sum of two chiral bosons, a left-moving and a right-moving boson. And FP here is the space of representation of one of the say, the left chiral boson, where P corresponds to the zero mode momenta of that boson, and F bar P is the space of representation of the right chiral boson. And the zero modes, P and P bar, since the boson is compact, they take discrete values, which are precisely given by the square roots of these expressions. I'd just like to spend some time and show you some numerics. So even at a small lattice site, when n is equal to 16, one can already see how the low energy states organize into the conformal towers. So here I've plotted the excitation energy above the vacuum, and I've just normalized it by this factor n over 2 pi v Fermi. And so here you have a primary state corresponding to W equals to 0, and the descendants are approximately an integer apart in the normalized energy. Here it's not quite an integer, but it's expected that as n goes to infinity, these dots will sort of move towards this line. Among the dozen or so lowest energy states that I've plotted here, one also finds the conformal primary with corresponding to the winding number W is equal to -1 and its sort of tower of excitations. And also the conformal primary with W is equal to +1. Here there's some ambiguity. In particular, for instance, one could take this state to be the conformal primary with W is equal to +1, and so this it's a bit ambiguous which one of these states I decided to label W is equal to +1, at least from the study of the spectrum of the Hamiltonian. However, in the limit n goes to infinity, when these dots approach the line, then the ambiguity will vanish. Now the XXZ spin chain, up until now, up until around 15, 20 years ago, it sort of formed the basis of our intuition of scaling in critical integrable spin chains. However, 15 years ago, a remarkable observation was made by Jacobson and Salyor regarding another lattice model that's governed by this Hamiltonian. So the Hamiltonian is slightly more complicated than the XXZ spin chain Hamiltonian. In particular, apart from nearest neighbor interactions, there are also next to nearest neighbor interactions here, for instance, and also interactions involving free spins. Moreover, there's also this I here, so that the Hamiltonian is not a Hermitian matrix. If one were to go diagonalize it just for some small finite n, one would find that the eigenvalues are complex. However, in the scaling limit, it turns out that the energies become all real. At least for the low energy part of the spectrum, the energies become real. What Jacobson and Salyor noted was that in the parameter domain, where this gamma is from 0 to pi on 2, the spin chain is critical, and the spectrum of conformal dimensions, unlike the XXZ spin chain, which is labeled by just the discrete number W and a Z, it also has a continuous variable S that can take any real number. Hence, this way, the space of low energy states in the scaling limit is contains this sort of direct sum, direct integral, sorry, apart from the direct sum, contains a direct integral over all possible values of S. What motivated our study of the spin chain was this paper, 2012 Physics Review Letters paper, of Gleb, Jacobson, Salyor, about the spin chain. And here they claim that the scaling limit of the spin chain is governed by a conformal field theory known as the Euclidean black hole nonlinear sigma model. The Euclidean black hole nonlinear sigma model and its Lorentzian version is a rather famous CFT. It was first studied in the 90s in connection with, it models a quantum fields traveling in a black hole background. So it was studied in the context, for instance, of string theory. Later, it attracted attention in the ADS CFT correspondence, and around the same time also in developing methods for studying non-rational conformal field theories. This is one of the simplest, apart from Liouville field theory, one of the simplest non-rational conformal field theories. So spin chain systems, there are a large number of very powerful numerical and approximate and analytic techniques for studying integrable spin chains. On the other hand, the situation with QFT is a bit more complicated. So quantum field theories are not that well understood, and there aren't that many perturbative techniques for studying quantum field theories. That way, if there is a quantum field theory that appears in the scaling limit of a spin chain, one can obtain non-trivial results on the quantum field theory by studying by analysis of the spin chain and then by taking the scaling limit of the spin chain and analyzing that. So these sorts of spin chains, which exhibit a continuous spectrum of scaling dimensions, which would correspond to some non-compact, non-rational CFT, a CFT with a continuous spectrum of scaling dimensions, they would be of interest, for instance, the ADS CFT correspondence where these non-compact CFTs appear. And also, they could potentially have condensed matter physics applications to the description of disordered electronic systems. So motivated by this paper, we performed a extensive study of the lattice model. And our study is contained in these 3 papers, together with my collaborators Bajanov, Kaval, and Lukyanov. I would just like to give you a quick summary of the results, of some of the results that we obtained and some of the work that we did. First of all, we completely described the low energy spectrum at large N. The reason that this is actually a more difficult problem than for the XXZ spin chain, and the reason is because since the spectrum is continuous, there's some non-trivial density of states, and the fact that there's a density of states which needs to be calculated makes this problem quite a lot more difficult than the case of a spin chain with a discrete spectrum of scaling dimensions. Moreover, we found that there was a discrete component in the set of conformal dimensions, which was missed by previous authors and previous scientists, and we characterized it as well completely. We also considered the Hermitian structures, which are consistent with the integrable structures, and analyzed what happened in the scaling limits. This point, although it's rather technical, it was very important, proved crucial for the verification of the Eklund-Jacobson-Salyor conjecture. The scaling limit of the spin chain is governed by the Euclidean black hole nonlinear sigma model. We found that formally the spectrum of the Euclidean black hole nonlinear sigma model CFT and the spectrum of conformal dimensions in the spin chain, they formally coincide. However, it's not correct to say that the scaling limit of the lattice system is governed by that CFT. For example, although the algebra of conformal symmetry for the spin chain and the underlying the critical behavior of the spin chain and that of the Euclidean black hole CFT, they do coincide, they're in different regimes. And finally, we sort of proposed a modification of the conjecture of Eklund-Jacobson-Salyor and proposed a CFT that would describe the universal behavior of the spin chain, which is based on a gauged SL2R Weizmann-Witten model with certain reality and boundary conditions imposed on the fundamental fields. In my talk, I'm just going to focus on the computation of the density of states, which itself is rather interesting. But first of all, before I start going to these details, I should explain a little bit where the spin chain comes from. Because, for instance, just looking at the Hamiltonian, it's completely not obvious that it's integrable, for instance. In order to do that, let's just remind ourselves what the connection is between the XXZ spin chain and the six-vertex model. So the Boltzmann weights of the six-vertex model are usually encoded in this R matrix, which is the trigonometric solution of the Yang-Baxter equation, with anisotropy gamma and spectral parameter beta. This R matrix is a 4x4 matrix, and it can be considered as acting in the tensor product of C2 cross C2. And from it, one constructs the row-to-row transfer matrix, where one multiplies the R matrices along one of the spaces, one of the C2s, the first one, which is known as the auxiliary space, and tensor products over the second space, over the so-called quantum space. Then, after this multiplication, one takes a trace over the auxiliary space. This corresponds to the imposing these periodic boundary conditions. And because we impose actually quasi-periodic boundary conditions, take into account of that, one needs to introduce this exponential here. And then the transfer matrix is a 2 to the power of n times by 2 to the power of n matrix, corresponding to sort of n tensor products of two-dimensional spaces. Although it's a rather complicated matrix, it turns out that the Yang-Baxter equation for the R matrices, this local relation, implies that the transfer matrix commutes for different values of the spectral parameter, beta and beta prime. So it forms sort of a large commuting family of operators. Then the XXZ Hamiltonian is just given by the logarithmic derivative of the transfer matrix near at some particular value of beta. Beta is equal to 0. So for the spin chain that was considered in the works of Euclid, Jacobs, and Salur, it's built from the transfer matrix, which is almost identical to the one for the homogeneous six-vertex model, except that here the spectral parameter is staggered, plus I pi over 4 and minus I pi over 4. So this staggering has the interpretation of introducing inhomogeneities, which are different for the odd sites and the even sites. And this vertex model is known sort of as the inhomogeneous six-vertex model. Nevertheless, despite this staggering of the spectral parameter, this proof here that the Yang-Baxter equation implies that the transfer matrices commute still follows through almost unchanged, so that this is an integrable model. And the Hamiltonian is just given by the logarithmic derivative of two of these transfer matrices, again at some special parameter, special value of the spectral parameter. So there were many works devoted to the analysis of the low energy spectrum of the lattice model. And the final result is this formula over here. P and P bar here are similar to the same big P's and big P bars for the XXZ spin chain. They're given by these numbers, where Z and W are integers and K is just the twist parameter going into the boundary conditions. Here, in order to avoid factors of pi as much as possible, an isotropy parameter gamma has been swapped for n. So we use n rather than gamma for the anisotropy. And since gamma ranges from 0 to pi on 2, n is just a number that's greater than 0. Some real number that's greater than 0. Now the difference between this formula and the corresponding one for the XXZ spin chain is this middle term over here, 2s squared over n. It turns out that this s squared is actually depends on n, first of all, which is very, very different. And it turns out to be related to the eigenvalue of a certain operator that belongs to the commuting family. It's constructed just by the transfer matrix, and s is essentially the logarithm of the eigenvalue of the quasi-shift operator. So just to reiterate, if you have some better state, an eigenstate of the commuting family, and one calculates the energy for large n, it will follow this formula where this S is the eigenstate of the operator B, called the quasi-shift operator. Just to give some, so the quasi-shift operator has a meaning, has the interpretation of being the transfer matrix of a homogeneous six-vertex model on a 45-degree rotated lattice, where the spectral parameter beta is fixed to some value, and it commutes with this inhomogeneous six-vertex model on the staggered lattice by virtue of the Yang-Baxter equation. Let me explain. I guess this will be sort of to the experts. I'd like to explain to the people more involved in this field how this extra parameter S arises in the formula for the low energy spectrum. Again, I'm gonna use the analogy of the XXZ spin chain Hamiltonian. So it's well known that the Bethe-Ansatz equations for the XXZ spin chain are given by this formula. So this equation is a coupled system of transcendental equations for m coupled systems. J here travels from 1 to m, for m unknown variables beta j. So it has some discrete number of solutions. And each one of these solutions to these transcendental equations is in one-to-one, well, the intuition is that it's in one-to-one correspondence to the eigenstates of the XXZ Hamiltonian. And once you know the Bethe-Ansatz solution corresponding to a particular eigenstate, you can in principle calculate any eigenvalue. Well, you can calculate any eigenvalue in the commuting family, and for example, the energy for a beta state corresponding to some solution of the Bethe-Ansatz equations is given by this formula. So it provides another way of studying the spectrum of the Hamiltonian without diagonalization. So for the ground state, the beta roots turn out to be all real and they're distributed in this way. And as n increases, they tend to become more clumped up in the center here. The way the quantum numbers in the XXZ spin chain manifest themselves in the solution, the corresponding solution of the Bethe-Ansatz equations is, first of all, SZ is just related to the total number of beta roots, and a half minus SZ. As for the quantum number W, it's sort of more complicated, and I don't want to talk about it here. I'm just going to assume for now that W is equal to 0. And these L and L bars, so the pattern of beta roots, this for the ground state L and L bar is equal to 0. However, the pattern of beta roots for non-zero L and L bar looks similar to this one, except with the roots at the edges being perturbed. So for instance, the case L is equal to 2 and L bar is equal to 0, there's this root here, there will be a hole over here, and this root will be to the left. So the pattern will look similar, but with a different configuration here at the edge. And for instance, L is equal to 0 and L bar is equal to 2, then be this root would be over here, and this edge would be the same. The Bethe-Ansatz equations for the staggered case are almost identical. I've just I've written them and I've just highlighted and read the differences. So the difference is only in the Bethe-Ansatz equations is only in the source term. There's an n divided by 2 instead of n, and instead of I gamma over 2 and beta j, there's a fact, basically an overall factor of 2 multiplying the argument of the cosh. Also, the formula for the energy is slightly different and differs by factors of 2, roughly speaking. The eigenvalue of the quasi-shift operator can be just calculated by this formula. Now, although the Bethe-Ansatz equations are practically identical, apart from this small modification of the source term, the structure of the solutions are completely different. For the ground state, instead of the beta roots being on the real line, they actually cluster around 2 lines. So imaginary beta is equal to 0, and imaginary beta is equal to pi on 2. Once again, SZ is related to the total number of beta roots as before, as for the Heisenberg XXZ spin chain. L and L bar correspond to these sort of excitations. So the pattern of beta roots for L and L bar not equal to 0 would be sort of perturbed at the edges with these states, there being holes sort of, and these states being moved to the left, for instance. However, now that the beta roots lie on two lines, gives us the opportunity of introducing excitations where, for instance, the number of beta roots on the top line and on the bottom line are disbalanced. And so, for instance, this is the ground state, right? And this would be a state where one of the roots has gone to the top and there's more beta roots on this top line than the bottom line. And the net effect of this is that there is an extra quantum number, which is called m, which is just equal to the difference between the number of beta roots on the line imaginary beta is equal to pi on 2 and 0. So this extra quantum number, this extra degree of freedom is what gives rise to the extra parameter S in the 1 over n corrections to the energy for the low energy spectrum. Gleb and Saliora in their 2008 paper, they considered these sort of states, which look similar, the states with L over bar W equals K is equal to 0, where the beta roots are distributed along 2 lines. and the number of beta roots on the top line and the bottom line could be different. And the difference is encoded in this quantum number n. And through the study, they found that the value of S, the logarithm of the eigenvalue of the quasi-shift operator, essentially, has the following behavior. So it's given by, it goes as 1 over the logarithm of n. So when n is very large in the scaling limit, the difference between S for one of the states and the neighboring state where m is just increased by 2 goes as 1 over the logarithm of n. So S essentially becomes densely distributed along the real line. Here I've drawn the distribution of S for the case n equals to 400 as an illustration. The density can be read off from this formula. It's divergent, and it goes as 2 pi over the logarithm of n. It's just a simple consequence of this formula. However, this leading sort of divergent behavior fails to capture the fact that the distribution here is not uniform, obviously. For instance, it's more dense over here than say, out at the edges. So the density of states is a non-trivial function of S, and this non-trivial part is captured in this order 1 correction over here. Gleb, Jacobs, and Salor managed to compute the density of states exactly for the case L bar is equal to 0. Their intuition was that this formula for the corrections to the energy, 1 over n corrections to the energy, resembles that of a CFT made up of 2 bosons. A compact boson whose chiral components, so the compact boson can be written as a sum of 2 chiral bosons, and P and P bar would be the 0 modes of the chiral bosons. And since these P and P bar are discrete values, given in terms of SZ and W, this boson is compact. And S, since it's a continuous and can take, in principle, any real number in the scaling limit, would correspond to a non-compact boson. The large n behavior, the asymptotic formula describing the large n behavior of S, resembles that of a quantization condition for the free particle confined to a potential value of length proportional to the logarithm of n. Then, as in usual quantum mechanics, sort of a more accurate quantization condition can be achieved by taking into account, via sort of a semi-classical approach, the phase shift that the particle picks up at the turning points. This would lead to the quantization condition of this form. And when delta of S is equal to, when n is very large, for instance, and delta of S is finite or is negligible compared to the logarithm of n, this equation would just reduce back to the previous equation I showed on the previous slide, that S goes as pi over 4m divided by the logarithm of n. Then, in their 2011 paper, Gleb, Jacobs, and Salor found that they took the phase shift from the papers of Molasena, Guriason, and Hanani, Prezes, and Trust, which studied the Euclidean black hole nonlinear sigma model and related models. And they took this formula and they plugged it into this equation here, and they found that it perfectly reproduced numerical data. It perfectly coincided with the numerical data. Now, once you have such a description of the large asymptotic behavior of S, the density of states can be simply computed. And basically, it's computed by differentiating the left-hand side with respect to S, roughly speaking. So it's given by this sort of divergent behavior plus the derivative with respect to S of the phase shift. And here I've presented some numerical data to illustrate this, the presence of this term in the density of states. So I've plotted rho zero regular, which is just rho zero minus this divergent part. And here is data taken from the spin chain where I've calculated the density using by means of the Bethe-Ansatz equations, and I've superimposed it on this line. There is some sort of difference here when S becomes sufficiently large, but it's expected that as N becomes larger, sort of the two lines will match for larger and larger S. At this point, I just like to present our result for the which is the density of state computed for any L and L bar, just at this moment, and then later on in the presentation, I'll discuss it and explain how it was derived. So this rho zero of S was the result by is the density of states for LL bar equals 0 that was found by IQFT and Salur. And this part is sort of rather trivial. Part to L is the number, is a combinatorial factor. It's the number of bipartitions of L. The non-trivial dependence on the levels is contained in this extra logarithm, where this curly D is given by a product which contains the level in the upper bound and also in the exponent. The product is over this A, integer A. Let's just remember that P and P bar are related to the eigenvalue, the integers SZ and the winding number W. Number of bipartitions of L it's convenient to define it by the generating function. So part 2 of 0 is 1 and part 2 of 1 is 2 and so on. And D of L, this extra integer carrying the exponent, the generating function is similar to that of part 2 of L, except there's this extra sum over here. So for the remaining part of the talk, I'll try to explain the intuition of the logic of how we obtain that formula. And the natural way of approaching the problem is to try to generalize this quantization condition, to try to use the intuition of IQFT and Salur and generalize it to any level, LL bar, or to any Bethe state. Now, at this point, we need to sort of make things more precise. So when we, here, N is a parameter, for instance, and S here is considered to depend on N. So when we mean S depends on N, what we're doing here actually is instead of considering Bethe state psi, we're actually considering a family of Bethe states with this parameter N. Then we're calculating the eigenvalue of the quasi-shift operator on that family, taking the logarithm, and this way we obtain the function S of N. So even in writing this equation, we're sort of assuming, we're identifying states at different lattices, for different lattice sizes, and constructing an RG trajectory, assigning an N dependence to the eigenstates of the spin chain. Now, in general, for a general lattice system, there's problems. It's actually, this procedure in itself is problematic. So for instance, the Hilbert spaces Hn and Hn plus 2 and so on are not isomorphic. The dimension is 2 to the power of n. So this procedure only makes sense for the low energy part of the spectrum. It's clear how to assign a scale dependence for the ground state or for the vacuum in any sector for that matter. However, in the case considered here, where the states are densely distributed, so how to identify states for different spin chains in different Hilbert spaces that are densely distributed seems to be a non-trivial problem. Here, it can be solved, or an RG trajectory can be assigned in a meaningful way, and it uses integrability and it uses the existence of the Bethe-Ansatz equation in particular. And I don't want to discuss it, I just want to point out that it's a whole, it's a separate issue. Secondly, it seems very, it might seem tempting to treat M as a quantum number that's fixed. However, if we keep M fixed, then S for any RG trajectory would always tend to 0. So we would always obtain a state with 0S in the scaling limit. That's why in order to achieve a non-trivial scaling limit where S becomes some constant, instead of assigning S an n dependence, we have to assign M, the quantum number M, an n dependence. So we identify states here and here with different values of M. And it should be assigned so that it grows as the logarithm of n in such a way that S reaches a finite limit as n goes to infinity. This way, the quantum numbers describing the state are L, L bar, S, Z, W, and the limiting value of S, that is S star. And in what follows, I'm going to be a bit loose with notation. I'm actually going to use the same symbol for S and S star. So strictly speaking, S is the eigenvalue of the quasi-shift operator computed on a finite lattice, and it depends on n, and S star is its limiting value. But in what follows, just to simplify notation, I'm going to use the same notation for both of these things. And if there's an issue, I guess I'll point it out. So the RG trajectory psi that's labeled by these quantum numbers becomes a state in the tensor product of the Verma module of the extended algebra of conformal symmetry, where the delta and delta bars are given by these expressions. So from the eigenvalue of the energy, I can only extract delta minus C over 24, which is given here. Also, let's just recall that P and P bar are related to SZ and W. These are integers, SZ and W in this way. So the quantum numbers W and SZ are contained in P and P bar. Now, an extra fact that doesn't follow from my discussion is that this psi infinity actually has the form of a tensor product of two states, each one of which belongs in the right chiral space, left chiral space, and one belongs in the right chiral space. Then the phase shift delta would be a function of psi cross psi bar, which would be a function of these states occurring in the scaling limit. So in order to obtain the correct formula for delta, one would of course need to study first of all these states psi and psi bar. Now, similar to how on the lattice the beta state diagonalizes an infinite family of commuting operators, these states psi are also expected to diagonalize an infinite family of commuting operators that live in the Verma module, that act in the Verma module of the extended algebra of conformal symmetry. This integrable family, infinite number of commuting operators acting in the Verma module, they would sort of correspond to the scaling limit of the transfer matrix. Therefore, one comes to the natural problem. In order to characterize the state psi, one comes up against the problem of how to construct the family of commuting operators in the Verma module, in the chiral Verma modules that are inherited from the lattice, from the spin chain. This is, a rather difficult and technical point. And just, we use the method of the ODE IQFT correspondence, and just to motivate that method, let me, I'd like to talk about some opera. I'd like to make a small aside just to motivate the ODE IQFT correspondence. So the commuting family of operators for the lattice model contains the transfer matrix T of beta, but there are also other commuting operators, most famously the Baxter Q operators that also commute with the transfer matrix and with each other. And in particular, these commuting families of operators, they satisfy some operator valued relations. The famous one is the Baxter TQ relation, but there's also the Q-Wronski relation here. And as Baxter points out in his book, it turns out that the TQ relation can be used to reconstruct the eigenvalue, along with some analyticity conditions, such as the fact that Q is a polynomial in e to the negative 2 beta, and T is also a polynomial. TQ relation itself can be used to reconstruct the eigenvalues of the transfer matrix and the Q operator without any reference to the explicit construction. In fact, the Bethe-Ansatz equations can be just derived from this relation, assuming some extra conditions on Q such that it's a polynomial of order n divided by 2 minus z. In the scaling limit, these operators T and Q become infinite dimensional matrices acting in the chiral Verma module, and one could obtain, depending on how one organizes the scaling limit, one can obtain operators acting in the right chiral space or the left chiral space, V of delta bar. And similar to the lattice, they also obey a bunch of operator relations which are analogous to the TQ relation on the lattice and the Q-Wronskian relation on the lattice. If these relations are specialized to a common eigenvector of this commuting family, then it becomes a functional relation for the eigenvalue. And it turns out, similar as on the lattice, that assuming some analyticity properties, it is possible to reconstruct T and Q just from the functional relations and the analyticity properties themselves. As a result of these works, a remarkable observation was made that the functional relations for the Q and T operators, such as the Q-Wronskian relation and the TQ relation, could be realized in terms of connection coefficients of certain linear ordinary differential equations. And because the functional relations and together with analyticity properties are so constraining, it was found in these works that one could actually prove that, for instance, the eigenvalue of the Q operator is equal to the connection coefficient of a certain linear ordinary differential equation. Further development along these lines led to something called the ODI QFT correspondence. It's a correspondence between an integrable structure and a certain class of linear ordinary differential equations. So for every common eigenstate in the integrable structure, there is a certain linear ODE on the ODE side, and the eigenvalues of the Q and T operators for that common eigenstate are given in terms of the connection coefficients. And the ODI QFT correspondence provides a set of very powerful analytic and numerical tools for studying integrable structures in CFT, because it just reduces a problem in quantum field theory, basically, to a numerical integration of an ordinary differential equation, which is very straightforward and a well-known problem. From our analysis of the spin chain, we managed to propose the ODE for the ODI QFT correspondence for the integrable structure that occurs in the scaling limit of the staggered six-vertex model. The linear ODE has this form, and in particular, there's a regular singular point at z equals to 0 and an irregular singularity at z equals to infinity. So near the singular point, near the regular singular point, one can introduce a basis of solutions, provided that P is not a half integer or integer, via the asymptotic as z goes to 0. Then near the irregular singular point, one can always introduce the decaying solution. Then the Wronskian, the connection coefficients in this case would be given by this by this expression that this is just a Wronskian. It doesn't depend on z. It only depends on p, s, and mu, and n, which are the parameters of the ordinary differential equation. So the statement for LL bi is equal to 0 is if this constant c is taken to be here, and this mu is related to beta, the spectral parameter for the spin chain in this way, then the scaling limit of the transfer matrix, which includes this extra shift of the spectral parameter, is given by this ratio. And at the moment, this looks like a rather nasty sort of expression. However, it's something that, for instance, the left-hand side, you can just compute using the Bethe-Ansatz. The right-hand side requires you to numerically integrate a differential equation, one can compute the left and right hand side and see that they are indeed equal. And that's what we did, for instance, to check it as a numerical check. There's a technical assumption that n is greater than 2. If n is smaller than 2, this scaling limit actually diverges and one needs to introduce subtractions, which results in a more complicated formula, just to ensure the convergence of this limit, that this limit exists. Then in order to obtain the ODE IQFT correspondence for any L and L bar, there's a general method that was first introduced in these works for the quantum KdV integrable structure, in that one introduces singularities into the ordinary differential equation, which are apparent, in the sense that every solution is single valued in the vicinity of WA. So because these singularities are apparent, it means that the monogamy properties of the ordinary differential equation are changed, and so the functional relations for the spectral determinants are the same, they stay the same. And the fact that these singularities are apparent is a special property, and if these WAs are general, typically one would, if one was, for instance, to construct a solution locally near WA, one would find a logarithm appearing. So this, that they're apparent results in a coupled system of algebraic equations of WA, which has a discrete number of solutions. And it turns out, just from numerical work, that the number of solutions is given by pi to A, L. Then the statement is that for a better state labeled by L, L bar, SZ, and W, there exists some solution of these algebraic equations such that the scaling of the transfer matrix is given by exactly the same formulas as for L, L bar is equal to 0. So I'm running a bit of time. I should be probably finished by now. So I'll just, I'm gonna probably have to skip a few slides and speed up a little bit. So far, we've discussed the scaling limit of the transfer matrix that results in the operator acting in the right chiral subspace, and it's described by an ODE that depends on P, S, and W1 to these solutions of the algebraic system. One can also organize the scaling limit differently to obtain an operator that acts in the right chiral subspace, and it's described by a different ODE, where P is replaced by P bar, and W1 bar, WL bar satisfy also a set of algebraic relations which are identical to these, except P is replaced by P bar and L is replaced by L bar. This way, the scaling limit of the beta state psi m is given by these two chiral states, each of which is labeled by these apparent singularities. And the, let me see. And the upshot basically is that the spectral determinants, given the psi n, the spectral determinants encode all the information about the eigenvalues of the integrals of motion, and the phase shifts, these coefficients here, which can be determined, which can be interpreted as the eigenvalues of the reflection operator, go into the phase shift. Enter into the phase shift here. So we found that the quantization condition could be generalized by including these including the eigenvalues of the reflection operators into the logarithm, and and that essentially results in this formula for the density of states. So finally, let me just summarize. I guess I'm a bit over time. So I discussed the problem of computing the density of states for a critical integrable spin chain possessing a continuous spectrum of scaling dimensions. And in my talk, I tried to emphasize the role played by the quantization condition and the fact that the quantization condition contains the eigenvalues of certain operator in the integrable structure that's known as the reflection operator. And the application of this to the Euclidean black hole conformal field theory is that the density of states on the spin chain basically coincides with the density of states in the Euclidean black hole CFT. And the calculation of this density of states for the Euclidean black hole CFT was an open problem since the original works of Mulder, Sonoguru, and Son, and Hanani, Prezes, and Trust that originally constructed the partition function for the Euclidean black hole nonlinear sigma model. Okay, thank you very much for listening. That's all I wanted to say.
Okay, thank you very much, Gleb. We've got some time for questions. Might need to unmute yourself to ask a question.
So I have a couple of naive questions.
Go ahead.
So what happens in the isotropic limit?
In the isotropic limit, you mean when delta n goes to gamma goes to 0? Yes, you mean?
Yeah, that's right.
So when n goes to infinity, the parameter n here goes to infinity. Yes.
Yeah.
Because gamma is pi over n plus 2. So in the isotropic limit,
not necessarily in terms of the density of states, but in terms of this non-compact boson and so on.
The isotropic limit corresponds to the sort of classical limit. The parameter 1 over n can be identified with the Planck constant, so that the n goes. So in terms of the CFT, so that when the n goes to infinity, that corresponds to the Planck constant going to 0. So what in particular are you interested in?
So how much of this survives? I mean, is it important that it be anisotropic, or does this non-compact boson survive even in that limit?
So I assume that's, we've always taken n to be generic. We didn't specifically consider the limit n goes to infinity. I assume that things simplify because it's sort of like a classical limit. But of course it would require special attention or maybe a detailed, which we didn't do.
Okay. And then another naive question, have you thought about an extension to higher rank?
So of course, that's an extremely interesting question, I agree. But first of all, it comes with some technical difficulties. You mean higher rank, not SL2, you mean like SL3, for instance, spin chain, yes?
Well, or some other. Yeah, I'm actually thinking along the lines of, well, I mean, this model is closely related to D22. And you could then consider D2N. Okay,
so one of the issues with going to higher rank is that the ODE IQFT correspondence is not that well understood for higher rank Lie groups. It's understood well for the SL2 case, but not in that. So that part could break down, and also the complexity of the problem, of course, increases. Technically, the complexity increases. But other than that, I mean, do you know personally of a spin chain of higher rank that has a continuous spectrum similar to this one, or it's definitely an interesting question to study, of course.
I'm thinking it should be D2N, but
I'd like to know that that's an interesting question, and nobody really knows. Nobody really studied except Salor, Jacobson, and their collaborator. What is happening with the alternating, or maybe more complicated alternation, like a n-fold period of alternation. So the space of these continuum limits is not explored. So we don't know. So, you know, for 30 years, we are just all these spin chains is something boring, you know, we understand everything better and that, but now something new comes out. So if we do the trivial thing, just alternating, we go sometimes not, we are getting additional degree of freedom in the continuum limit. And so, well, there are plenty of interesting thing to explore. And Gleb didn't mention that we have like a paper which give a comprehensive analysis of algebraic structure for the six-vertex model. So inhomogeneous, what we can tell algebraically without even consideration of the continuum. And so that analysis need to be repeated for other groups, for D to M in the first instance. So.
Could I ask a fairly naive question? Well, since I don't know much about the area, this is Nalini. First of all, I gather you're in Germany, so thank you for being available at 3 a.m. your time to give a talk. What I was wondering was about the ODE-IDM correspondence. If you look at the linear problem you displayed a few slides ago, for example, where the poles are, you know that these are related to isomonodromy type problems.
Yes.
In the sense that if you have an additional deformation of WA, what's called WA, I think it is in your slide, you get equations like the Punleve equations. I'm wondering what that deformation means here. I mean, you don't necessarily want to take it, I understand, but does it have a physical meaning in this context? What is going on with isomonodromy, if there was such a condition here?
So first of all, could you just explain more precisely what type of deformation you mean? I just didn't quite understand.
If you take that linear problem, the ODE that's on your slide, and you now consider the possibility that the locations of the poles of the coefficients may change with another parameter. And then you demand that the monodromy problem, that is, if you take, for example, your solutions of this particular ODE, and then you go around in the complex plane, in the Z plane, around the point, the location of the pole WA, you will get some kind of change, potentially, around the locations of these places. And if the center of your point, your position, if that path is taken around a point that's moving with another parameter, independent of Z, and you can ask that the structure of your solution space stays the same. So the monodromy data remains the same. If you do that, then you automatically get the Punleve equations as the governing equations for the locations of these kinds of poles. So I'm wondering what the meaning of that condition might be in this context. Perhaps there's a physical meaning here that I don't really know about, or whether there's an interpretation that you already have that might link in with that point of view.
So the best I can give you is just, I know for a fact that the Punleve equations, I prefer not to comment. I'm not sure. I haven't thought about this question. Sorry.
Anyway, that's another direction that might be of interest to somebody in the future.
Okay, thank you.
It's not always happens. So we have some the equations which are written here. So basically, you can't move. So we have a discrete set of singularities. There are some degenerate equations where you can move this. But in general, so that's algebraic equation, system of cubic equations, and the number of solution is the number of partition of some integer. So they're not moving anywhere. So I know
When you
that.
say cubic, do you mean that algebraic condition involving WA below this ODE? Is that cubic?
Yes, yes.
Ah,
Yes.
I see. You've got WA times WA squared and so on.
Yes,
So
and
you
so
have a
it's a
condition.
system of cubic equations.
I see. That's why you're saying they don't move.
No, you just solve this algebraic transcendental equation, find the solution, plug into the differential equation, and you can see that the solutions are what is it, entire function. They have poles, but there are no branching point.
I understand, but there might be slightly.
Yeah, I know. I think.
For example, n could change. I don't know whether n is constrained to be.
I know the classical story about this fourth pole equation. What is it called?
Yes, Fuchs's equation.
Yeah, Fuchs equation and how it is related to monodromy. It's all related.
Yes.
And I think some time ago, Alexander Itz told me that he understood that connection. And he promised to write a paper. But I think a few years passed. I haven't seen the paper, but I can ask him what's the story.
Well, there are many people in the audience of this talk who know this relation with Fuchs as well. So
no. He meant to apply it here, but I don't know what came out.
Thank you.
Do we have any other questions there before we conclude? A quick look around. No questions or anything. So on that note, I think we'll thank Gleb for his talk, and he can look forward to the rest, I think.
Thank you, Gleb.
Okay, thanks a lot, Gleb. Thanks, everyone.
All right, good night.
Well, thank you. So just a quick reminder, next session is on the 9th of March. And we will have Dr. Croydon from Kyoto University talking about invariant measures for the KDV and prototype integrable systems. Thanks everybody for attending the talk today. Bye.
Bye.